to take a look at non-Euclidean geometry and other geometries. So we're going to identify the basics of elliptic geometry, hyperbolic geometry. We're going to create fractal figures and create tessellations. So this is going to be a little break from our typical algebra here. So after thousands of years of accepting Euclid's geometry as the only possible geometry, in the 1800s, mathematicians and scientists started to question whether or not that's really the only possibility, or if there were other systems which his principles didn't apply, and that's how we got started with non-Euclidean geometry. And so there's some key terms within any geometry. So we use the word postulate, which is basically an assumption that underlies something that can't be proved. So we've observed something thousands of times and we assume that it's true, but we can't necessarily prove it. So that's a postulate. In Euclidean geometry, an example of this is the parallel postulate, which says given any line M that has a point A on that line, there's only one line parallel to it. I cannot geometrically prove that, but by observation and definition of a parallel line, it becomes an underlying assumption. Mathematicians have spent 2,000 years trying to prove this postulate and have been unable to, which is why it remains a postulate. What's happened, though, is as they've tried to solve it, they've run into rules that don't necessarily follow what Euclid set out in his geometry. And elliptic geometry is one of those examples. So in elliptic geometry, we're doing geometry on a sphere. So a great circle is a circle on the sphere that has the same center. So if you think about the globe, that would be the equator. So the equator would be a great circle because it has the same center and it moves across there. The same thing applies to the latitude. So when you've got 0 degrees, that would be another great circle. An interesting thing that happens with elliptic geometry is that we can put triangles on a sphere. And so you may think, why on earth would somebody put a triangle on a sphere? Well, that's how our cell phones work. That's how satellites work. That's how radio signals are transmitted, is through triangulation. That's how your GPS works. And so there is a reason we want to put that, because we need 3 points that communicate to one another. And if I connect those 3 points, they're going to form a triangle. And when I do this, the sum of the angles isn't that fixed number. It depends on the area of the triangle. And as the area gets smaller, the sum gets smaller and smaller of all 3 angles, but it never quite reaches 180 degrees. If you find it hard to imagine that, consider that basically we're doing the math where we live here on Earth. And so all the math that we do that's related to the real world does follow principles of elliptic geometry. Hyperbolic geometry is based on the assumption that given a line and a point that's not on the line, there's an infinite number of lines that are parallel to M. So this is going to contradict the postulate we learned earlier. And this happens on a funnel-shaped surface known as a pseudosphere. And so the line that we're talking about is illustrated here on our pseudosphere. In hyperbolic geometry, the shortest distance between 2 points is not a straight line, but instead it's a curve. And the curve of the pseudosphere actually arcs inward instead of outward like on the sphere. So if you see those, they're convex angles. So the sum of the angles in a triangle in this geometry is less than 180 degrees because it has those inverted convex angles. Fractal geometry is another area that was born, and fractal geometry makes geometric figures by using shapes that are repeated. So these are a lot of the brain teasers that you see that pop up on how many ways can you make a triangle. If you go to Cracker Barrel, the game at Cracker Barrel that's placed on the table utilizes fractal geometry. In this case, an equilateral triangle was used repeatedly, and this is called the Sierpinski triangle. The repeating process where the shape is constantly being repeated is called a fractal. And the repeating process that leads to the fractal is an iteration. Just like if you iterate on something, you're constantly improving it. In this case, we're adding on to it, which improves it. Computers generate fractal figures very easily and very quickly, utilizing copy and paste. Additionally, in nature, we find a lot of things that represent fractals like ferns, flowers, mountains, etc. that can be duplicated or at least simulated using fractals. So there's some really interesting art projects that you can do with your students with this type of geometry. Iteration is one feature that makes geometric figures fractals. The second feature that it must have is self-similarity. So if you look back at the fourth picture of the Sierpinski triangle example, you'll note that the portion that was the lower right triangle is the picture directly above it, and you'll see that this portion of the fractal looks like a miniature version of the whole thing. So let's look at how we would actually create another fractal. So we would start with an equilateral triangle, and we would replace each side with like the star, the point, and then we would keep repeating that process. So iterations means repeating, and that's how we actually wind up with the conch snowflake. A tessellation is a similar idea, but it's more related to tiling. So mosaic tile is an example of tessellations. These patterns use the same geometric shape, and they don't have any gaps in between them. So polygons that can form tessellations. Tessellations can be formed by any polygon whose sum of the angles around the vertices is 360 degrees. It just means you're going to have to do a puzzle. So a tessellation can be made from these steps. So you draw your polygon, so we use the square. Cut the square from the top to the bottom using any design so that it divides it into two shapes. Move the left-hand piece and put them back to back and tape them together. Once you have that done, then you can again cut that piece, put them back to back, tape them together by creating the figure. Then, once you've done that process twice, you can start tracing it onto a sheet of paper so that they line up like puzzle pieces. And you'll see these exact figures have no gaps in between them, and they're the repeated figures, so it's considered a tessellation.